In this video, I want to prove a few properties of the powers of a group element. Throughout this video, I'm just going to let G be a group, and anytime I refer to A, this is going to be an element of our given group. The first, if the order of my element A is n, then there are exactly n different powers of A to the 0, a squared, a cubed, all the way up to an minus 1. So what this theorem says is that every positive or negative power of A is somewhere in this list. Not only that, but all of these things in this list are different from one another. So let's look at proving this. Let's start by proving that every power of A needs to be in this list somewhere. Let's consider a to the m, a random power of A. The division algorithm tells us that m is equal to nq plus r, where r has to be between 0 and n. Using this, we're going to write am. This needs to be the same as a nq plus r. Properties of exponents tell us that this is a to the nq, a to the r, which can also be written as a to the n to the q power, a to the r, once again using properties of exponents. A to the n is the identity, so I have the identity to the q power, a to the r. And the identity to any power is just the identity, so I finally just end with a to the r. And since r has to be between 0 and n, including 0 but not including n, we know it has to be on this list. The next thing we want to do is prove that everything on this list is distinct and different. There's no repeats. So let's suppose it's not true. Let's suppose that AR is equal to a to the s, where r and s are distinct integers between 0 and n minus 1. So I have two on my list that are the same. Let's suppose s is the smaller of the two. Then we have that 0 is less than or equal to s is less than r is less than n. And as a result of that, 0 is strictly less than r minus s, which is strictly less than n. Well then, if I do AR, as to the minus 1, this should be equal to as to the minus 1, since AR is equal to as by assumption. On the left-hand side, we have AR, a to the minus s. On the right-hand side, these are inverses, so we can see this is the identity. Using properties of exponents, we have a to the r minus s is equal to e. However, this gives me a contradiction. By this, r minus s is a positive integer less than n, but n is, by definition, the smallest positive integer such that a to the n is equal to the identity. So n is the smallest thing with this property that says I can raise a to that power and get the identity. So this would give me a contradiction. So therefore, they must all be different. While my previous theorem dealt with finite order, now let's deal with the case of infinite order. If a has order infinity, then all the powers of a are different. Let's suppose it's false. Let's suppose a to the r is equal to a to the s. Well then, I can rewrite this as a to the r times a to the s to the minus 1 is equal to a to the s, a to the s minus 1. So I multiply both sides by a to the s minus 1. Using properties of exponents, the left-hand side can be simplified to a to the r minus s, and the right-hand side is the identity. But now I have a raised to a finite power is equal to the identity, and that contradicts the fact that a has order infinity. The order infinity means there is no positive integer such that a to that power is equal to the identity. So I have my contradiction. The only way this would work is r minus s is equal to 0, or r is equal to s. For the last thing I want to prove in this video, let's suppose the order of my group element A is equal to n. Then we have that a to the t power is the identity if and only if t is a multiple of n. Let's start by letting t be a multiple of n. We'll say t is equal to nq. Then we want to prove that a to the t power is the identity. Well, a to the t powered would be the same thing as a to the nq. Properties of exponents say this is the same thing as a to the n to the q power. A to the n is the identity, and the identity to the q power is e. So if t is a multiple of n, then we do get back to the identity. Now we need to go the other way. Let's suppose a to the t is equal to the identity. The division algorithm then gives us that t is equal to nq plus r, with 0 less than or equal to r less than n. Well, then we know that e is equal to a to the t. A to the t can be rewritten as nq plus r. Properties of exponents say this is a to the n to the q power times a to the r. We already know a to the n to the q power is the identity. So we get a to the r at the end. So now I have the a to the r is equal to the identity. We also know that r is between 0 and n, including 0 but not including n. By definition of the order of a being equal to n is the smallest positive integer such that a to the n is equal to the identity. So that tells me that r has to either be greater than n or it must be 0. Since this is impossible, we must have that r is equal to 0, so t is a multiple of n.